All right. So we'll start by taking some questions from the previous homework assignment. So if you have things that you'd want to talk about or ask about, certainly we can take a few questions here to start. So if you do have something that you want to talk about, you can type into the chat and we'll kind of handle those one at a time. If you don't, that's okay too. Like, it's no pressure to do that. But we'll take a few minutes here at the start if anybody has anything that they want to talk about. So Josh, you're talking about worksheet 2, I assume, since we have...
Yes.
Okay. So 13 or 15 is perfectly fine. We can realistically, we could do both of them without a whole lot of problem. So if I look at 13, I have these two fractions that I need to add together. Now, there's no obvious identity that I can use here. I mean, the only thing that really is accessible to me is that cosine is equal to 1 over secant. But now I'm making fractions inside of fractions, and that just feels like it's going to be kind of a mess. So I'm probably going to avoid doing that. Rather, what I would say is I would want to start by just making a common denominator to add these two fractions. So 1 minus cosine and 1 plus cosine are relatively prime. There's no common factors inside of those. So to make a common denominator, I'm just going to multiply the top and bottom of one by the other. Just like in your Algebra 3-4 class, if you had a rational expression with like a 1 minus x as the denominator and a 1 plus x as the denominator, the least common denominator would be 1 minus x times 1 plus x. Same idea here. So if I do that, I'm going to have cosine times 1 plus cosine x plus, got the x there, plus cosine x times 1 minus cosine x. All over, when I FOIL that out, I get 1 minus cosine squared x. I hope that's okay that I skipped the foiling there. So if I look at 1 minus cosine squared x, and I look at my identity sheet, just grab that. I have something there that I can use. So if I look at P1, if I say subtract cosine squared from both sides, I get that sine squared is equal to 1 minus cosine squared. So this is what I'm going to use to turn the denominator of that into sine squared. And then in the numerator, I'll just do my distributing. And if I combine like terms in the numerator, I have a plus cosine squared and a minus cosine squared. So those are going to combine to give me 0. And then a cosine x plus a cosine x is just going to be 2 cosine x. And now what I'm going to do is just kind of break this up so I can write this with no fraction. So what I'm going to do is I'm going to write this as 2, and then I'm going to write this as cos x over sine x, because I have an identity for that, and then 1 over, I have an identity for that. So if I look at my identity sheet, Q2 sine over sine is cotangent, and if I look at R4, cosecant is 1 over sine. So I can call this 2 cotangent x cosecant x. And that's probably as good as I can do. Now, Josh, the other one you wanted to look at was 15, right? So here, again, I have two fractions added together. And you could start by making a common denominator. It wouldn't be wrong to do that. But I have a suspicion we can do a little bit better. So what I'm going to do is I'm just going to think about this to start with no fractions. Or well, or think about it this way. And you'll see why in just a moment, because I'm going to use Q1 to rewrite tangent squared as sine squared over cosine squared. And rewrite cotangent squared as cosine squared over sine squared. And now when I multiply, those reduce. So I'm left with 1 over cosine squared plus 1 over sine squared. So that's already quite a bit better, right? Now, there's no identity here that's going to help me right away, because all I can do with cosine squared is like turn into 1 over secant squared. I don't really think that's a great idea. Or 1 minus sine squared, which again, like, it's not going to make finding a common denominator here any easier. So what I'll just do is I'll make a common denominator. So I'll multiply the top and bottom of the first fraction by sine squared over sine squared, and the top and bottom of the second fraction by cosine squared over cosine squared. So now I have one fraction, which is simpler than two fractions. In the numerator, staring at me in bright flashing lights, sine squared plus cosine squared is just 1. And then if I just write this as two separate fractions, I can use my reciprocal identities to rewrite 1 over cosine squared as secant squared, and 1 over sine squared as cosecant squared. And that's as good as you can do. And we got this into one thing, right? It's a product, which is better than a sum, and there's no fractions in it, which is better than having fractions in it. So really that's the best answer to end up with. Can't get any simpler than that for this problem. Are you happy with those, Josh? Here's yeah, okay. Perfect. Does anybody have anything else before we move on today? If you do, just go ahead and put it in the chat. If you don't, that's perfectly fine. No big deal. We can always come back and take more questions later, another day, another time. So if you guys feel okay moving on, we can move on. No problem at all. Okay. Wanting to look at 26. So initially this looks quite confusing because we have two different trig functions in the problem. And there's no good way then to apply like an inverse, right? Well, the trick is I can turn this into a single trig function by dividing both sides by either sine or cosine. I'm going to choose to do cosine. So that gives me sine over cosine is equal to 1. And I know from my identities, one of my quotient identities says sine squared over cosine squared is tangent. Oops, I meant sine over cosine is tangent. And there's now the way I can proceed. So note this is the same problem now as number 17. So if you're able to do 17, you can certainly proceed from here. We'll continue to go ahead and do that though, but I just wanted to point that out. That if you were doing your homework and did notice that like, oh, this problem turns into the same thing as one of the previous problems, you can just state that and just copy the answers if you wanted to. All right, so tan inverse of 1, the places where tangent is equal to 1 is where the aim on the unit circle. That happens at pi over 4 and 5 pi over 4. That's my answer for A. For B, all I pi k's. And that's my answer for part B. I could do a little bit better, because if we notice, like on the unit circle, pi over 4 is here, and 5 pi over 4 is there. So if I go pi units from this answer, I run into the next answer. If I go pi radians from that answer, I run into the first answer again. So really, I into 1 that instead of the answers being 2 pi apart, are just pi apart. So that would be probably how the answer would look on an answer key or on a multiple choice test or whatever. Would I mark it wrong if you gave the answers with 2 pi k's in there? No, not if you had all the answers. It's still the same thing. It'd be like marking it wrong if you wrote 2/4 instead of 1/2. It's still the same. So C is the interval from negative 2 pi to positive 2 pi. Well, I know that my answers from 0 to 2 pi are still answers from negative 2 pi to 2 pi, because 0 to 2 pi is a subset of negative 2 pi to positive 2 pi. And I'm also going to have answers that are coterminal to pi over 4 and coterminal to 5 pi over 4. And I can get those and I want just by subtracting 2. So 2 pi, or 1/4 pi minus 2 pi is negative 7/4 pi. And 5/4 pi minus 2 pi is negative. And if I subtracted 2 pi again, these would both be too small. They'd be less than negative 2 pi. So I know that those are my only answers. E, we're looking for negative pi to 2 pi. Or to 4 pi, excuse me. So I know that 0 to 2 pi is still a subset of that. So my answers from part A are still good. I look at my other answers from part C, and if there's any of them that are bigger than negative pi, I'll take those. So like negative 3/4 pi is an answer that'll work, but negative 7/4 pi is too small, right? That's less than negative pi. Deal with that. And then I just have to worry about the stuff from 2 pi to 4 pi. So to find those answers, I'm just going to take these answers from 0 to 2 pi and look at the things that are coterminal and bigger. So I'll be adding 2 pi to each of those. So 1/4 pi plus 2 pi is 9/4 pi, and 5 pi plus 2 pi is 13/4 pi. And those would be my answers for part D. And these should be the same answers that you would have gotten for number 17. Again, this problem really turned into the same problem as 17 once we did a little bit of rearranging in the beginning. Okie dokie. All right. So today we're going to talk about proving trig identities. So just like in geometry, what we're talking about doing is a proof. Unlike in geometry, these are not things that we're going to be justifying with theorems. These are going to be more like an algebraic proof where we're just going to string together a bunch of equivalent statements like equal signs, basically. And what we'll use to justify the equal signs is either basic algebra things like factoring or combining like terms or making a common denominator or things like that, or using our identities. So those are going to be our primary tools in doing these proofs. But before we get into doing some examples, I just want to give some guidelines that are often going to be helpful. And the only requirement here is the first guideline. So the other ones are all kind of flexible or more like hints. But the first guideline is something that shown here. So the first guideline says that you can only work on one side of the problem. So you're either going to pick the left-hand side or you're going to pick the right-hand side. And the only work you can do is on that single side. And you're not finished until, if you pick the left-hand side to start with, until you've changed the left-hand side into the right-hand side. And we'll do a bunch of examples here to kind of get you familiar with that. But what this basically boils down to is you're not allowed to do things to both sides of the equation. That's not okay to do. And it's not okay to like work a little on one side, work a little on the other side, and meet somewhere in the middle. That's not going to be okay to do. So once you've picked a side, you have to work only on that side. You can't like quit halfway through and be like, you know what, I'm going to but you can't like meet in the middle. You have to kind of start all over again. So typically, you'd want to begin with the more complicated side and try to turn it into the simpler side. When we say complicated, so like more terms, so things added or subtracted from each other is more complicated than, you know, a single term with a bunch of things multiplied or divided. Just like when we did the simplifying trig expressions, you want to end with something a little bit simpler. So the next hint would be if you get stuck, you can try to rewrite everything in terms of sines and cosines. That's often quite helpful. So if you have two fractions and you want to combine them together, you can do that by making a common denominator. And then using that difference of squares factoring pattern can be quite helpful in setting up the Pythagorean identities. So if you are going to try to use one of those, that's a very helpful thing to kind of keep in mind. And the last thing is just kind of be attentive of where you're trying to get to. So what does that other side look like that you're trying to get to? Often you can gain a little bit of insight about what you might want to do by looking at that. So I'm going to drop in the identities again because we're going to be referring to those during the course of these problems. Oops. Okay. Let's say that we have the identity tan x plus cotangent x is equal to secant x times cosecant x. So the first thing we'd want to do is we want to pick the side of the equation that we want to work on. And typically you want to pick the more complicated side. In this case, we have two things added together on the left-hand side, and then we have two things multiplied together on the right-hand side. So on the left-hand side, we have two terms, and on the right-hand side, we have one term. The more complicated side has more terms, so I would start on the left-hand side with the tangent plus cotangent. That doesn't mean that you have to do that, but in this problem, it makes things much, much easier if that's what you choose to do. So next thing I would do is look to see if there's anything algebraic that I could do with tangent plus cotangent. They're not like terms, so I can't add them together as they're currently written. So I'm kind of stuck there, right? There's no algebra that I can do. The next thing I would do is look for an identity. So there's no identity that I have that relates tangent and cotangent together other than the reciprocal identity that I'm not too keen on trying to use here because I don't have a good feeling about that. Rather, what I would use is my quotient identities for tangent and cotangent, because I would like to rewrite them using just sines and cosines. So I'm going to do that. So this was me using Q1, and that was me doing Q2. Now I'm going to list the name of the identity that I use while I'm doing the notes. That's not really a requirement for you. What I'm really looking for when you do these proofs, though, is clarity in what you're doing. So don't do too much in one step. If you're doing something kind of sneaky, if you want to label the identity that you used, please do that. But a proof is about like communicating with the reader why something is true. So really kind of keep that in mind and try to keep things like neat and organized and not do too much in any step to where like if you do like 4 or 5 things, like it's really hard for the reader to kind of follow what it is that you've done, especially if you give no explanation. So I'm going to go, whenever I use an identity, I'm going to label that I used an identity. Mostly for you guys, when you're going back to read these things, you know what I did. And if you'd like to do that, I think it's an excellent idea. But I wouldn't mark it wrong on a test or whatever if you elected not to do that. All right. So we have these two fractions. So I have two terms that are now fractions. I can now add these together by making a common denominator. So rewriting these in terms of sines and cosines was quite helpful for me because it allowed me to, a way to combine these two trig functions together. So the common denominator I would need to make is cosine times sine. So we'll multiply the first fraction by sine over sine, and the second fraction by cosine over cosine. So that's going to give me sine squared x over sine x times cosine x. And notice here that I'm not going to list any identity because I didn't use an identity. I just did some basic algebra stuff by making a common denominator. Now, if I look at the numerator of my new single fraction here, I see sine squared plus cosine squared. That I recognize as P1. That's the first Pythagorean. I know that sine squared times cosine squared is equal to 1. And then I'm just going to do some algebra here. And I'm just going to rewrite that as 1 over sine x times 1 over cosine x. Again, I didn't use an identity here, so there's nothing really to label. I've just rewritten, a single fraction as the product of two fractions. And the reason I did that is because I recognize that 1 over sine is cosecant. I think that's R4. Yep. Just wanted to double check that before I wrote it down wrong. And then 1 over cosine is R5. That is secant. And that's what I had on my original starting place. So I'm done. These verifying problems should feel very similar to the simplifying problems that you've already worked on. I think the verifying problems are easier because you know specifically what it is that you're trying to end at. The simplifying is not always entirely clear what it is you're supposed to be ending with. So I think that in a way these ones are actually a little easier because you know what the answer is supposed to be. Your job is just to kind of fill in the details of how to get to that answer. So let's do a couple more. I think I have 4 that I've outlined in my notes to do. And that'll be it for today. All right. Oops. Okay, so here I have two fractions that are equal to each other, and at first glance it's not entirely clear which side would be the more complicated side, and to some extent it doesn't really matter, but the thing that I would say is the left-hand side is more complicated than the right-hand side. Because the right-hand side, because there's just a single thing in your denominator, you could break that into the sum of two fractions really easily. You can't do the same thing to the left-hand side, because you can't write cosine x over 1 minus sine x as like cosine over 1 minus cosine over sine. You can't do that on the left-hand side. On the right-hand side, though, you could write that as 1 over cosine plus sine over cosine, because those have common denominators. You can do that. So I'm going to work on the left-hand side. And first thing I would do is check to see if there's any algebraic thing that I can do, and there's obviously not, right? Like we have a fraction without any like terms anywhere, so there's no reducing I could do to that fraction. So the next thing maybe I would look is say, okay, well, maybe I can put it all in terms of sines and cosines, and that might elicit some kind of a, something to me. And if I look at that, well, it's already in terms of sines and cosines, so there's nothing really to do there. Okay, well, I'm running out of hints here. So what I end up at is 5, where it says the identity a plus b times a minus b equals a squared minus b squared. Well, if I look at the denominator here, I have an a minus b, right? That's something minus something. If I multiply the top and bottom of that by 1 plus sine squared, that'll get me the 1 plus sine squared in the numerator that I need. So let's kind of see what happens. That seems like maybe that's going to be a good idea. So that's what I'm going to do. Let's just multiply the top and bottom by 1 plus sine. So you could distribute the cosine through, but I'm not going to, because I know that I'm supposed to have a 1 plus sine x in the denominator. So I'm reasoning that at some point that cosine is going to cancel out of there. In order for me to cancel that out, it's got to be in a factored form anyways. So I'm not going to bother to distribute that cosine through. If you had thought to do that, you wouldn't really make a problem for it. You just end up having to factor it back out later, which is not a big deal if that happened. And then the denominator, I'd have to FOIL that out. When I FOIL that out, I get 1 minus sine squared. Aha! 1 minus sine squared, that rings a little bit of a bell, right? If I look at that first Pythagorean, if I had subtracted sine squared from both sides, I get cosine minus sine squared. So I can replace the denominator in my problem with just cosine squared. And that's like a modified version of P1. So I'm just going to call that P1 star. The star just indicates that I had, rearranged P1 a little bit in order to use it. Now if I look, I notice that I have a cosine times 1 plus sine in the numerator and a cosine squared in the denominator. So since everything is kind of in a factored form, I can reduce. So the cosine on top is going to cancel with one of the cosines in the bottom. And I'm left with 1 plus sine over cosine, which is exactly where I had started, or what I wanted to end with, excuse me. Are we doing okay so far, guys? Okay. So if we move on to our next example. I have 1 minus cosine x times 1 plus cosine x over cosine squared x is equal to tangent squared x. So first thing I should do is pick the side to work on, and I hope that it would be pretty obvious that the left-hand side is clearly the more complicated side, right? The right-hand side is a single trig function, which you can't get a lot simpler than that. So if I start on the left-hand side, I would start by looking for is there any algebraic thing I can do? And I have this 1 minus cosine times 1 plus cosine that is screaming to me, please FOIL me out. And that's probably what I would do first. So if I multiply that out, I get 1 minus cosine squared. So I FOILed that out and some stuff canceled, and I'm left with just 1 minus cosine squared. And we've seen that already today, right? If I go back and I look at my P1, if I had subtracted cosine squared from both sides, I know that sine squared is equal to 1 minus cosine squared. So I can use that to rewrite my denominator as, or my numerator as sine squared. So I'm going to call that P1 star 2 because it's the second modified version that I made. So that gets me to a single term in my numerator, which is better than 2 terms. And then I recognize, oh, sine over cosine, that was one of the quotient identities. Sine over cosine is equal to tangent. So sine squared over cosine squared must be tangent squared, which is what I was trying to get to. So I'm done. That one maybe looked a little worse than it actually was. My last one, or my last example for you guys, is this monstrosity. So first thing we should do is choose a side to work on. Now it certainly seems like the right-hand side is the more complicated side, and I would agree with that. I think that this one turns out to be a little bit easier if you picked the other side, but I don't know why you would think to do that without a bunch of experience and intuition anyways. So I'm going to choose to work on the right-hand side here because I think that that would be the obvious choice for most of us just starting out. So the first thing I'm going to do is I'm going to look for, is there any algebraic thing to do? So if I look at this big quantity here that's in the parenthesis, I have sine squared minus 2 sine to the 4th plus sine to the 6th. I notice there that I have a greatest common factor of sine squared. So I'm going to factor that out. And that's awesome that I noticed that, because if I compare now to the left-hand side where I'm trying to get to, I notice that I have a sine squared in the left-hand side also that I'm supposed to get. So I have that part. Here I have cosine to the 5th. Here I have cosine. So this piece in the middle somehow needs to turn into cosine to the 4th, right? So that I can multiply it to the other cosine to end up with the cosine to the 5th. So we just need to kind of sort out how that's going to happen. So if I look at the thing that's in there, 1 minus 2 sine squared plus sine to the 4th, it looks a little like a polynomial, right? So let's say that we let a equal sine x, so it looks a lot more like a polynomial. Oops. So it definitely is a polynomial, right? Once I've made that substitution. And if you remember, this kind of a polynomial should jump out to you as being factorable. This would have been something you did last year in your Algebra 3-4 class. You should recognize this polynomial is in the quadratic form. I can tell that because I have a constant term, and then the degrees of the other two terms, 1 degree is twice the other. So if I think about making a second substitution, I'm going to call b equal to a squared. That gives me 1 minus 2b plus b squared. So this is now definitely quadratic, and it's definitely something I can factor. I just need to find two things that multiply to give me 1 and add to give me -2. Well, that's just -1 and -1. So I can write this as 1 minus b times 1 minus b. And again, we're not trying to factor for b's, so that's really 1 minus a squared times 1 minus a squared, because b is equal to a squared. But we really don't want a's in this either. We're trying to have just x's. Well, I know that a is equal to sine x, so I have 1 minus sine squared x, and then 1 minus sine squared x, and that's really what I want. So if I rewrite this, then I have sine squared times 1 minus sine squared x, 1 minus sine squared x times cosine x. How are you guys doing with that? Now that was kind of complicated, what I just did there. Were we able to follow that? If you have a question on what we did, please unmute and say so. If you're fine, you don't have to do anything. You can just sit and wait for the next step. But all of your screens on my Zoom call have gone black, which makes me nervous that I've lost everybody. Can somebody type something into the chat if they can still hear me and see me? Okay. So Josh says we're still here. You guys got it? Okay. So I'm going to continue, as it seems like, we're still kind of here. And I don't know why I can't see anybody's faces anymore, but it happens. Okay, so good. We're still seems like most of us are here and can see, which is fantastic. Okay, so I noticed here, after we did that tricky factoring, that I'm left with this 1 minus sine squared, which I remember we had run into earlier. That 1 minus sine squared is equal to cosine squared. So I'm going to go ahead and use that identity to make that substitution. So that was P1, what we called P1 star, because it was a modified version of P1. And that gives me sine squared. That one turns into a cosine squared. That one turns into a cosine squared. And now there's still my cosine. And then if I just combine like terms, cosine squared times cosine squared times cosine is cosine to the 5th. And that's what we're looking for. So we're done. Okay. So that does it for chapter 5. What I'd like for you guys to work on here is the problems on 47 to 62 in the homework set. These are all verifying problems of a variety of difficulty. They're not necessarily arranged from like hardest to easiest, but there are some, ones that may be trickier or easier for you depending on, like what you see. Sometimes it's easy to see what to do as you get more and more experience. Sometimes they're going to be hard, and that's okay. At some point, you just got to kind of try things. If you're not sure what to do, there's no shame in like trying something and getting nowhere and going, well, I guess that wasn't a great idea, and scrapping it and trying something else. That's certainly something that you'll probably need to do as you learn how to do these and get more and more familiar with them. So try not to get frustrated if that's happening to you. It's okay. It's pretty normal. So this is where we're going to stop, and I'm done with you guys for the day. In general, when we're doing these Zoom lectures, I'm going to shoot for really them lasting under an hour. I think that an hour is a long time to sit and watch me do math without having like a little bit more give and take. So I'm going to do my best to try to keep things, kind of brief and under an hour, so to give you guys some time to work on the homeworks and the problems and whatnot on your own, and just get up and move around and like not be glued to your computer screen. So this is going to be it for today. So you guys are dismissed. Reminder to you before you go that I do want you to type bye into the chat before you sign off the Zoom call. But we're done doing things. So unless you have specific individual stuff that you wanted to stay and talk to me about, you're free to go. Just remember to type bye into the chat before you leave. But have a good day. Stay safe.
Hello, I just wanted to talk individually about like the old problems that we did.
Sure.
So like 1 through 14, I was absent when we did those, and I've practiced them a little bit, but I'm still pretty lost.
Okay. Were there something that you wanted to look at specifically? I know 1 through 14, but that's it.
So we've already done. Yeah, we've already done 1 through 2.
Okay.
So if you could do like, I think we did 6 in class, so if you could do something like 5, and then
Sure.
one of the bottom ones, that would be great.
Yeah, absolutely. So I'll do 5. And while I'm working on that, if you can pick one from the bottom that looks good, we can certainly do 1 or 2 of those. That's not a big deal. Okay. So we're looking for the value of the other.
Okay. I think I think that they're the same as what we on the. So I'll just. I'm not sure if they're the same or not.
So with these problems 3 through 6, you can do them 2 different ways. So one way you can do it is you can do it the way that we've done before. So we know that cotangent is negative in quadrants 2 and quadrants 4. And we know sine is negative in quadrant 3 and quadrant 4. So the triangle that we're going to draw is going to be in quadrant 4. So I know that cotangent is x over y. So I have 5 and 9. I just need to assign the negative sign to the correct place. Since we're in quadrant 4, I know the y-coordinate is the part that should be negative. And then I can use the Pythagorean theorem to find the hypotenuse here. So 5 squared plus 9 squared is 106. So that's the square root of 106. And then we can use our basic definitions now of like sine, cosine, tangent, opposite over adjacent and all that jazz to fill out the rest of these. Just like we had done before, right?
Yeah.
Okay. Alternatively, we could have done this using identities. So for example, I know that cotangent is equal to sine over cosine. Right? Oh, I'm sorry, cosine over sine. So I know cosine over sine is equal to -5/9. And because I know sine is negative, we're told in the problem that the negative sign should go on the 9. Okay with that? Maybe not. Let's not. No, let's not. No. We can't do that. Let's not do that. We'll use one of the Pythagoreans to start. So they are. So that's sec or cosec. Okay. So I know that 1 plus cotangent squared is equal to cosecant squared. So I can say 1 plus -5/9 squared is equal to cosecant squared. So that's 25 over 81 plus 1 is 106 over 81. And if we square root both sides, we get plus or minus 106 over 81 is equal to cosecant. So I just made a common denominator there to get the 106 over 81. I just did it quickly in my head. And because cosecant is negative the same place sine is negative, I know that this is negative 106 over 81. Okay there?
Yeah.
Okay. And since I know sine and cosine or sine and cosecant are reciprocals, I can say that sine then is negative 81 over 106. And you'd rationalize the denominator there, but I'm going to not bother with it. Okay with that. Ooh, whoa, wait.
Yeah, I just gotta plug my tech.
These are supposed to be 9s. Sure. Okay. Sorry, those are supposed to be 9s because I forgot to square root the 9. Okay.
Oh, okay.
Yeah. So we have this answer. We have this answer. And we know cotangent from the beginning. Right away, I guess I could say that tangent is just going to be its reciprocal, right? So I have that right away. And the last thing I need is the cosine. So I can get that then by saying cotangent theta is equal to cosine theta over sine theta. So I have negative 5/9 is equal to cosine theta over negative 9 over the square root of 106. So if I multiply both sides by 9 over 106 over 1. I end up with positive 5 over 106 for cosine. And then secant is just its reciprocal. So you could do this all like with the identities also. It doesn't, I mean, in this one, the directions are such that it doesn't matter which way you would want to do that. But either way works.
Okay, thank you.
Yeah, of course. And you wanted to do one of these simplifying ones also?
I think so, because are these just the same as the ones on worksheet 2, or are they different?
No, it's the same idea.
Okay. I think I'd be good with these ones then, if it's the same idea.
Yeah.
Because there are a lot of new signs, but I think they're just random variables.
Correct, yes. So beta or y or whatever, they're just a variable name, like it doesn't really matter. You could put like a chicken there, like sign of chicken. The chicken's just a variable. It's a weird variable, but like whatever. Is that you're happy with that then?
Okay, I think I'm okay then. Thank you.
Yeah, you're welcome, Josh. Have a good morning.
You too.
Thanks.